There's something lurking at the edge of the universe. So rare, only 8 have ever been seen. They're enormous, perfect circles that glow in radio waves, unlike anything else in the cosmos. What are they? Where did they come from? And why do these cosmic rings defy everything we thought we knew about the universe? Get ready to meet the strangest, rarest phenomenon in all of astronomy: odd radio circles. So watch this video till the end and subscribe to the channel. Let's begin. Odd radio circles are among the rarest and most enigmatic objects ever detected in the cosmos. These aren't rings you could spot with the naked eye, or even through a regular telescope. These are immense, ghostly circles that only reveal themselves in the invisible realm of radio waves. First identified in 2019, ORCs instantly captured the attention of astronomers worldwide because, until that moment, nothing like them had ever been recorded in the vast catalogues of cosmic phenomena. Out of the countless billions of galaxies, nebulae, supernova remnants, and exotic objects mapped so far, just 8 of these colossal rings have been confirmed. Their rarity is almost absurd. Imagine searching the oceans for years and finding just a handful of bizarre, glowing whirlpools unlike anything described in textbooks. ORCs present as vast, faint halos, each one stretching across hundreds of thousands of light years, many times larger than our own Milky Way. Yet, despite their immense size, they remained hidden from view for the entire history of modern astronomy. What makes them even more astonishing is not just their shape or their scale, but the fact that they appeared only recently in our surveys, as if the universe had been keeping a colossal secret just beyond our technological reach. The first hint of their existence came from the Australian Square Kilometre Array Pathfinder, ASCAP, a cutting-edge radio telescope designed to survey the sky with unprecedented sensitivity. Researchers noticed something peculiar: nearly perfect rings that stood out sharply in the radio images, but were completely invisible at optical or infrared wavelengths. At first, these rings were so unexpected that astronomers double-checked their data, wondering if some kind of error or artifact could have produced such a perfect circle. But there it was, a gigantic, ghostly loop, glowing softly at radio frequencies and surrounded by the emptiness of intergalactic space. Soon, a few more were detected in different parts of the sky, each one displaying the same bizarrely circular appearance. Unlike supernova remnants or radio galaxies, which often show irregular or elliptical shapes, ORCs appeared as crisp, almost mathematically perfect rings. The cosmic census stood at just a few, with each new discovery sending ripples of excitement and confusion through the scientific community. The odds of stumbling upon something so rare are staggering. Billions of galaxies have been scanned, and yet only these few oddities have emerged. This rarity isn't just a quirk. It points to either an extremely unusual origin or an observational challenge that has prevented their detection until now. And as soon as the first papers were published, the race was on. What could possibly generate such immense, symmetric structures, visible only in the faint whisper of radio waves across billions of light years? Astronomers have encountered strange phenomena before: quasars, pulsars, fast radio bursts, but ORCs were a different kind of mystery. They didn't fit any existing model or prediction. There was no obvious process in the astrophysical playbook that would explain a lone, ring-shaped emission of such scale and symmetry. Even more intriguing, there seemed to be nothing similar anywhere near us. All known ORCs were located billions of light years away, as if the phenomenon belonged to an earlier epoch of cosmic history, or a part of the universe where conditions are radically different from our local environment. These discoveries upended assumptions about what could exist in the radio universe. Theorists scrambled to come up with possible explanations, while observers scoured old data and launched new surveys, desperate to find even a single additional example. In the world of astronomy, where objects are usually classified and understood within a few years of discovery, ORCs stubbornly defied easy answers. Their existence is an ongoing puzzle, a cosmic riddle with almost no clues. But how did such a dramatic revelation almost slip through our fingers for so long? What kept these gigantic structures hidden from the watchful eyes of generations of astronomers? The answer is as fascinating as the ORCs themselves, and it leads us to the very limits of our technological capabilities and the blind spots of our instruments. This is where the story of odd radio circles only begins to get more thrilling. If odd radio circles are so gigantic, why did we miss them for so long? The universe isn't exactly subtle when it comes to objects spanning hundreds of thousands of light years. So how did something that big, sometimes twice the size of the Milky Way, evade detection until the 21st century? The answer is buried in the history of radio astronomy and the limitations of our technology. For decades, radio telescopes scanned the sky, mapping out powerful sources like quasars, pulsars, and radio galaxies. But unlike these bright cosmic beacons, ORCs don't shout, they whisper. Their radio emissions are incredibly faint, so diffuse they barely rise above the background static of the universe. Older radio telescopes were simply too insensitive, too narrow in their fields of view, and too focused on pinpoint sources to notice these vast, ghostly structures. Most classic radio surveys looked for sharp, compact objects, things that stood out like lighthouses in the cosmic dark. They weren't optimized to catch gigantic, faint rings with low surface brightness. Even if an ORC drifted through a telescope's field, it would probably appear as little more than a ripple in the noise, easily dismissed as an artifact or interference. The sensitivity, resolution, and data processing needed to pick out an ORC just didn't exist until recently. Then came the new generation of radio observatories: ASCAP in Australia, Meerkat in South Africa, LOFAR in Europe. These telescopes didn't just collect more data, they revolutionized how we see the radio sky. Massive arrays of antennas worked together, imaging huge swathes of sky with unprecedented depth and clarity. Advanced algorithms sifted through terabytes of data, hunting for patterns that human eyes might never notice. When ASCAP began its EMU, Evolutionary Map of the Universe, survey, astronomers expected to find the usual suspects: radio galaxies, supernova remnants, maybe some new kinds of transient phenomena. But then the data revealed something so strange that it seemed like a glitch. Almost perfect circles, looming hundreds of thousands of light years across, faintly glowing against the darkness. It took repeated observations and cross-checks to confirm that these were real, not errors or random noise. In fact, the first ORC was nearly dismissed as a processing artifact. It took the persistence and skepticism of astronomers to rule out every possible mundane explanation: satellite interference, imaging error, gravitational lensing, even computer bugs. Only after all these possibilities were painstakingly eliminated did the reality set in. Something new had appeared in the sky. Why did it take so long to find them? Because until these deep, wide-field radio surveys, nobody was looking for such enormous, subtle features. For most of astronomical history, the tools just weren't up to the task. Even now, detecting ORCs requires the perfect combination of sensitivity, sky coverage, and careful analysis. It's entirely possible that dozens or hundreds have been hiding in older survey data, their signals simply too faint or too diffuse to be noticed until now. This also explains their apparent rarity. If you only look where your instruments can reach, you miss everything that lies below the detection threshold. Only now, as we push the limits of sensitivity, are these strange rings coming into view? And the process isn't automatic. Human skepticism and cross-verification are essential. Even a single missed step in data processing could turn an ORC into a ghost that vanishes with a new calibration. So, what exactly do these objects look like to astronomers using the latest radio telescopes? How do you identify a faint ring against a background filled with noise, confusion, and competing signals from a universe teeming with activity? What's the actual visual experience if you're the scientist who first opens a dataset and finds an ORC? So, what do odd radio circles actually look like to astronomers? In the raw data, ORCs are almost unsettling in their clarity, appearing as near-perfect circles, thin yet enormous, faint but undeniable. Unlike the tangled spirals of galaxies, the jagged remnants of supernovae, or the irregular shapes of most cosmic clouds, ORCs reveal themselves as geometrically pristine rings, each one stretching across hundreds of thousands of light years. It's this symmetry that first signaled to researchers that they had found something completely out of the ordinary. Imagine peering at a radio map of the sky, a chaotic patchwork of sources, bursts, and background fuzz, when suddenly a single vast ring emerges from the noise, hauntingly crisp in its outline. It's not a filled-in disk, not a random splotch or a lopsided arc. It's a halo, almost like the after-image of a stone dropped into water, but on a scale that defies comprehension. For astronomers used to irregularity and chaos, the perfection of an ORC is almost alarming. What's even more astonishing is how consistent this appearance is across all known ORCs. Whether viewed at higher or lower radio frequencies, whether imaged by ASKAP, MIR, KAT, or other arrays, these rings retain their fundamental shape, a luminous, nearly uniform ring with a diffuse interior and a sharper edge. Some show faint hints of structure, perhaps a brighter segment, or a subtle asymmetry. But the overwhelming impression is of a perfect, isolated circle. This shape is profoundly puzzling. In the natural universe, large-scale symmetry is rare. Explosions and outflows from galaxies tend to create blobs, cones, jets, or irregular shells, never crisp, standalone circles. Even the most dramatic supernova remnants look tangled and warped compared to the clean geometry of an ORC. In fact, astronomers routinely hunt for circular structures in radio images as a way to identify known phenomena, but nothing else matches the scale or regularity of these newly discovered objects. The geometry is so stark that it instantly raises questions about the physical processes at play. Are we seeing a true three-dimensional sphere projected onto the sky as a ring? Or is it a flat disk, a torus, or a shell seen edge-on? The prevailing interpretation is that we're observing a spherical shockwave, where the brightest emission comes from the edges due to a line-of-sight effect, much like how the rim of a soap bubble appears brightest. This, in turn, suggests an explosive or outward-moving event, but no known cosmic event produces a shell of this magnitude and perfection. The sharpness of the ring's edge is just as confounding. For a structure to maintain such definition over hundreds of thousands of light years, whatever caused it must have been both energetic and precisely symmetrical. Conditions almost never met in the tumultuous environment of the cosmos. And yet, every new ORC fits this strange template, as if following a rule book no one has ever seen. Astronomers have tried to match ORCs with catalogues of known objects: radio galaxies, starburst regions, galaxy clusters, but the fit is never quite right. Their size rules out ordinary supernovae. Their isolation and lack of optical counterparts make them unlike any known galaxy clusters or relics. Even rare phenomena like Einstein rings, caused by gravitational lensing, have different signatures and fail to explain the radio emission. Could the rings' uniformity and scale be telling us something fundamental about their origins? Does the symmetry point to a single cataclysmic event? Or could it hint at new physics? Perhaps a process that operates only under extreme specific conditions? The challenge is daunting. With so few examples, it's hard to establish patterns or find outliers that could give away the secret. Yet, the mere existence of ORCs forces astronomers to confront the possibility that the universe still harbors phenomena utterly outside our current understanding. The mystery deepens with every new discovery, each one reinforcing the sense that these rings are not only rare, but also unlike anything predicted by established astrophysics. If the shapes are a clue, maybe their locations in the universe offer the next piece of the puzzle. Where exactly do ORCs hide, and why are they so scarce? Where exactly do odd radio circles lurk in the vastness of the universe, and what does their bizarre scarcity tell us? As astronomers catalogued these haunting rings, one fact leapt out. Every single ORC detected so far lies billions of light years from Earth. Not one has been found in the nearby universe, not in our own galaxy, not even in neighboring galactic clusters. It's as if these colossal rings belong exclusively to a distant epoch, a part of the cosmos that has long since receded beyond our familiar surroundings. This distribution is as mysterious as the ORCs themselves. Normally, when astronomers discover a new type of cosmic object, there's some pattern, a tendency to cluster near certain galaxies, to appear in particular environments, or at a certain cosmic distance. But ORCs defy this logic. Their locations are random, isolated, and always unfathomably far away. Every time scientists map a new ORC, it's not in our cosmic backyard. It's in deep space, where light takes billions of years to reach us. Why does this matter? Because it immediately raises questions about both their rarity and their origin. If ORCs were common, we'd expect to see at least a few closer to home, among the millions of galaxies mapped in the local universe. Instead, we find none. This could mean that whatever process creates ORCs is not just rare. It's tied to a cosmic era or environment that simply doesn't exist anymore, at least not nearby. Some astronomers speculate that ORCs might be relics of ancient events, perhaps processes that were more common in the universe's distant past. If that's the case, it would explain why they appear only in remote regions, their light just now reaching us after traveling for eons across space. Alternatively, it's possible that the conditions needed to produce ORCs, extreme energies, rare galactic alignments, or unique environments, are found only in particular kinds of distant galaxies. Adding to the enigma, the areas where ORCs are detected often appear otherwise empty or nondescript in visible light surveys. There's no crowded star cluster, no massive galaxy group, no clear signpost marking where an ORC might form. They don't favor galaxy clusters, rich star fields, or active regions teeming with radio sources. Instead, they float in apparent isolation, like cosmic rings adrift in intergalactic voids. This spatial isolation is a double-edged sword for astronomers. On one hand, it makes ORCs incredibly difficult to find. Without a dense cluster of galaxies or a blazing quasar to point telescopes in the right direction, it's almost pure luck when a survey stumbles upon one. On the other, the emptiness around them rules out many mundane explanations. These aren't merely byproducts of ordinary galactic activity or chance alignments of foreground sources. Could their locations hold a clue to their origins? If ORCs are the aftermath of colossal explosions, mergers, or interactions between galaxies, perhaps those processes happened more frequently, or with more dramatic consequences, in the early universe. Alternatively, maybe the vast distances are an observational illusion, and ORCs closer to us are simply too faint, too diffuse, or too easily confused with other sources for us to pick out. But if that's the case, why don't we see even a hint of a nearby ORC? The statistical odds grow slimmer with every sky survey. 8 known, all far away, none close by. The universe isn't just hiding these things. It seems to have reserved them for its farthest, oldest realms. The implications are stark. Either ORCs are so staggeringly rare that the universe has produced only a handful, or our instruments, and perhaps even our understanding of radio astronomy, are missing a key piece of the puzzle. Their distribution hints that something profound has shaped their existence, something not at work in the familiar cosmic structures surrounding us. Yet even as we plot their positions on the map of the universe, a new question emerges. Do these immense radio rings surround anything familiar, or are they cosmic loners, detached from every known galaxy and object? That connection, or lack of one, could be the next step toward understanding what these eerie circles really are. Do odd radio circles surround anything familiar, or are they completely isolated cosmic phantoms? This is one of the first questions astronomers tackled after confirming ORCs were real. If you zoom into the center of an ORC using optical and infrared telescopes, you'll almost always find a distant galaxy sitting right at the heart of the ring. The alignment is so precise that it can't be coincidence. Statistically, the odds of 8 enormous rings all randomly centering on distant galaxies are effectively 0. But does this mean these galaxies are causing the ORCs, or are they just innocent bystanders caught in the middle of something much bigger? Most of the known ORCs have a galaxy right in the bullseye, detected only because sensitive surveys at visible and infrared wavelengths dig deep enough to spot these faint, faraway hosts. These aren't just any galaxies. They're often massive, and in some cases show signs of past mergers or unusual activity. But the connection is murky. Not every galaxy of the same type has an ORC, and not every ORC sits around a known kind of galaxy. The relationship is undeniable, yet maddeningly ambiguous. If these galaxies are the source, what could they possibly be doing to generate radio rings on such a monstrous scale? Nothing in the standard models of galaxy evolution, black hole activity, or starburst processes predicts the creation of a perfectly symmetric halo, hundreds of thousands of light years wide. No known supernova, gamma-ray burst, or galactic wind can. Explain the scale and uniformity seen in ORCs. Even the largest black hole jets and radio lobes are typically irregular, elongated, or bent, never circular and self-contained like an ORC. But perhaps these galaxies aren't just bystanders either. Maybe they're survivors of some ancient cataclysm, like a merger or collision that unleashed a shockwave so powerful it left a spherical radio imprint expanding through the intergalactic medium. If so, ORCs could be the ghostly aftermath of these events, with the host galaxy marking ground zero. Yet there's a problem. Galaxies collide and merge all the time, and if this were a common outcome, ORCs would be everywhere. Instead, they're almost non-existent, as if the exact circumstances needed to produce one happen only under extremely rare cosmic conditions. Another theory is that the galaxies at the centers of ORCs are home to extraordinarily active supermassive black holes. Maybe a gigantic outburst or a series of coordinated jets blew out an expanding shell of energetic particles, now glowing faintly in radio. But again, most radio galaxies with active black holes show completely different shapes. Lobes, plumes, jets, nothing as clean and circular as an ORC. And there are countless active galaxies with no ORC at all. It's also possible that the galaxy and the ORC are connected in a way astronomers don't yet understand. Perhaps there's an exotic process at work, something that occurs only once or twice in the lifetime of a galaxy, or requires an as yet unidentified set of circumstances. Massive reservoirs of gas, unusual magnetic fields, or a chain reaction set off by cosmic events from billions of years ago. And then there's the minority, a handful of ORCs with no obvious central galaxy, at least none visible with current instruments. Are these just the same phenomenon with fainter hosts, or are they an entirely different class of object? The uncertainty keeps astronomers guessing. The bottom line is clear. Most ORCs do seem to center on distant galaxies, but whether those galaxies are the cause, the result, or just caught in the cosmic crossfire remains an open question. What could possibly produce a structure this vast, this faint, and this precise? The quest for an answer pushes scientists to the very edge of what we know about galactic violence, cosmic shockwaves, and the unpredictable machinery of the universe itself. The next challenge: unraveling what kind of force, event, or mechanism could sculpt something so gigantic from the raw materials of space. How could the universe possibly generate a structure as immense as an odd radio circle, yet so faint that it's nearly invisible even to the most advanced instruments? When astronomers first grasped the sheer scale of ORCs, rings that stretch across hundreds of thousands of light years, dwarfing entire galaxies, the immediate response was disbelief. To create a feature of this size, something must have unleashed an amount of energy rivaling the biggest events in the cosmos. And yet, the result is not a blazing beacon or a field of chaos, but a ghostly, razor-sharp ring, detectable only in radio waves. The first and most obvious theory points to explosions. Cosmic outbursts so violent that their shockwaves ripple outward for millions of years, compressing and energizing matter on an unprecedented scale. In the universe, explosions come in many forms: supernovae, gamma-ray bursts, collisions between neutron stars, and titanic jets launched by supermassive black holes. All of these can shape the space around them, lighting up the interstellar medium and sending out waves of high-energy particles. But not one of these known phenomena matches the size or symmetry of an ORC. Even the biggest supernova remnants, for example, are tiny by comparison, mere pinpricks on the scale of these radio rings. So, could a galaxy-scale explosion be the answer? Some astronomers speculate that ORCs might be the result of events so rare and energetic that we've never witnessed one directly. Perhaps the merger of two massive galaxies, or the awakening of a supermassive black hole after aeons of inactivity. In this scenario, a cataclysmic blast could drive a spherical shockwave into the tenuous gas that surrounds galaxies in the deep intergalactic medium. As this shockwave expands, it would accelerate electrons to near light speed, trapping them in vast magnetic fields and causing them to emit the faint radio glow we see as an ORC. The brightness along the edge of the ring would simply be a geometric effect. Where our line of sight through the shell is longest, the emission appears strongest, giving us that sharp, circular outline. But if galaxy collisions and black hole eruptions can produce such rings, why aren't they more common? Mergers are frequent across cosmic time, and nearly every large galaxy is thought to harbor a supermassive black hole capable of extreme outbursts. The rarity of ORCs means there's something else required, some specific combination of conditions, perhaps the amount of available gas, the speed and energy of the explosion, or even the timing relative to the galaxy's evolution. It's possible that only certain kinds of mergers, involving very specific mass ratios or magnetic field configurations, are violent enough to create a shell on this scale. Or maybe only a handful of black holes are surrounded by enough raw material to interact with the blast in just the right way. Some models suggest that ORCs might be relics of ancient activity, echoes of a time when the universe was younger and more chaotic, when galaxies were colliding more frequently and the cosmic web was still settling into its present structure. In that case, the ORCs we see today would be fossil records, their shockwaves having slowed and faded over billions of years, leaving behind only the weakest traces of radio emission. This would explain why all known ORCs are so distant. We're seeing them as they were billions of years ago, and any that formed in the local universe have either faded beyond detection or simply never occurred under current conditions. Other possibilities push the limits of known physics. Some theorists have speculated about ultra-energetic events driven by exotic processes, maybe the annihilation of dark matter clumps, the interaction of cosmic strings, or some unknown instability in the fabric of space itself. While these ideas are tantalizing, they're far more speculative and lack the direct observational support that makes the explosion hypothesis so compelling. But with ORCs, astronomers can't afford to rule anything out. A third line of thinking looks at the environments around these rings. What if, instead of a single explosion, ORCs are the cumulative effect of repeated outbursts, multiple episodes of black hole jets, starbursts, or superwinds building up over time, inflating a shell that only becomes visible once it reaches a critical size? This would still require extreme energies, but could help explain why the rings are so well formed. If the energy injection is steady and spherical, the shell could inflate smoothly rather than breaking apart. Despite the variations, all these scenarios have one thing in common. They demand processes operating on scales and with energies far beyond what we normally observe in the universe. ORCs aren't just big, they're orders of magnitude bigger than anything produced by ordinary stellar explosions. To make a ring hundreds of thousands of light years across, a single event, or a series of events, must pump energy into a region of space as large as an entire galaxy cluster. This challenges not just our models of how galaxies evolve, but also the way we understand feedback between black holes, galaxies, and the cosmic web. And yet, for all their size, ORCs are almost impossibly faint. The radio emission from these structures is so weak that it lies on the edge of detectability even for the most sensitive instruments. This means whatever produced them not only had to be immensely powerful, but also left behind a ghostly, subtle signature, a contradiction that frustrates researchers. Why would such a violent event create something so nearly invisible rather than a blazing, long-lived relic? The puzzle deepens when you consider how energy from cosmic events usually dissipates. Shockwaves from supernovae and galaxy collisions typically break up into chaotic, filamentary structures. Magnetic fields twist and tangle, and relativistic particles lose their energy rapidly unless constantly replenished. Maintaining a smooth, symmetric shell of high-energy electrons over such a vast distance seems almost impossible. Yet that's exactly what we see in an ORC. Is it possible that these rings are the last, fading echoes of ancient cataclysms? Shockwaves from a bygone era when galaxies were more violent or cosmic structures were fundamentally different? Or are we seeing the signature of something even rarer, an event or process so unusual that only a handful have occurred in the entire observable universe? As astronomers hunt for answers, they're forced to consider every extreme. Maybe ORCs are smoke rings left by cosmic explosions so large and rare that we've only just caught their afterglow. Or maybe we're dealing with a new kind of cosmic process, one that requires a radical shift in our understanding of astrophysics. Each theory brings us closer to unraveling the truth, but for now, the sheer size and faintness of ORCs make them one of the universe's most dramatic and perplexing mysteries. But if explosions and shockwaves are the answer, what could cause such a powerful outburst, and why do these events seem so incredibly rare? Could ORCs be the remnants of singular explosive events on a scale we can barely imagine? Could odd radio circles actually be the smoke rings from gigantic cosmic blasts? Remnants of explosive events so powerful they leave marks on the universe itself? This idea quickly became one of the leading theories after the first ORCs were confirmed. There's an intuitive appeal to it. In nature, explosive energy often creates rings and shells, from the expanding ripples of a supernova to the shockwave from a volcanic eruption. If ORCs are on the same principle but scaled up to unimaginable proportions, what could possibly have triggered them? The most immediate suspect is the collision or merger of massive galaxies. These are among the most energetic processes in the universe. When two galaxies crash together, the chaos is total. Stars slingshot through space, clouds of gas compress and ignite bursts of star formation, and supermassive black holes spiral toward one another, often unleashing violent jets and outflows. In this scenario, the merging galaxies' energies could drive a colossal shockwave outward, inflating a shell of energized particles that radiate faintly at radio wavelengths for hundreds of millions of years. It's a compelling picture, but the numbers don't add up. Galaxy mergers are not rare. In the early universe, they were happening all the time. Even today, telescopes routinely capture the aftermath of galactic collisions. Yet, out of the billions of galaxies and countless mergers, only 8 ORCs have been found. If mergers were the primary cause, astronomers would expect to see these rings everywhere, at all distances, and in various stages of formation and dissipation. So what gives? One explanation could be that only the most extreme mergers, those involving especially massive galaxies, particularly dense halos of gas, or especially violent black hole activity, produce ORCs. These might occur only under certain conditions: the presence of huge amounts of intergalactic gas, perfectly tuned energy release, and perhaps a synchrony of events that rarely align. Maybe the galaxies have to be at a specific evolutionary stage or have particular magnetic field configurations for the resulting shockwave to manifest as a giant symmetric radio ring. Alternatively, it's possible that ORCs are formed by a different kind of explosion altogether. Some researchers propose that a single titanic outburst from a galaxy's supermassive black hole, something vastly more energetic than the typical jets or winds seen in active galactic nuclei, could create a shell of relativistic particles, expanding outward for millions of years before fading away. The problem is that even active black holes are common in the universe, and their known outflows typically produce jets and lobes, not neat spherical rings. The extreme rarity of ORCs also raises questions about their visibility. Perhaps these rings are short-lived on cosmic timescales, glowing in radio for only a brief window before fading into the background. If so, the odds of catching one in the act become astronomically small. Alternatively, it could be that ORCs form much more frequently, but only a few are oriented or positioned such that their radio emission aligns perfectly with our telescopes, making the rest all but invisible to us. There's also the issue of detectability. Even with the latest radio arrays, ORCs are faint, right at the limits of what our instruments can see. If there are more of them, lurking just below our sensitivity threshold, they might remain undiscovered until the next generation of telescopes, like the Square Kilometre Array, begins full-scale surveys of the radio sky. This would mean the observed rarity isn't a property of the rings themselves, but a reflection of how hard they are to find. Still, the smoke ring hypothesis remains attractive because it fits the observed features, symmetry, size, and the presence of a central galaxy in most cases. The energy needed to blow a radio-emitting shell hundreds of thousands of light-years wide would have to come from something cataclysmic, an event so fierce that it carves a nearly perfect sphere out of the intergalactic medium. The perfect ring shape could be the telltale sign of a spherical shockwave, bright at the edges because of the way the radio emission stacks up along the line of sight. But this leads to a deeper paradox. If such cosmic explosions happen at all, why so few? Why not a continuum of ring sizes and ages, fading in and out of detectability across cosmic history? And why do we not see even one ORC in our own local group of galaxies, or anywhere closer than billions of light-years away? Maybe the answer lies in the universe's evolutionary history. Perhaps there was an epoch, billions of years ago, when conditions were just right for ORC formation, when galaxies were larger, richer in gas, and more likely to collide with the exact violence required. Or maybe these events are linked to changes in cosmic magnetism, dark matter distributions, or yet unknown factors that only aligned briefly, never to be repeated. For now, the scarcity of ORCs stands as a silent testament to the rarity, or the observational elusiveness of the processes that create them. Astronomers are left with a cosmic riddle. If ORCs are remnants of ancient explosions, those explosions are not just powerful, but staggeringly rare. And the deeper they search for more examples, the stranger the mystery becomes. Is there another possible connection, perhaps to the monstrous engines at the centers of galaxies, the supermassive black holes whose outbursts can reshape entire galaxies? Could these rings be tied not just to the violence of galactic mergers, but to the secret lives of black holes themselves? Could odd radio circles be linked to the most powerful engines in the universe? Supermassive black holes lurking at the centers of distant galaxies? This is more than idle speculation. The correlation between ORCs and central galaxies is so precise that astronomers can't ignore it. And in nearly every well-studied case, that central galaxy almost certainly hosts a supermassive black hole, weighing millions or even billions of times the mass of the Sun. Supermassive black holes are anything but passive. When they feed on surrounding matter, They unleash furious winds, jets, and radiation capable of blasting apart whole regions of their host galaxy. The energy output can exceed the combined light of every star in the galaxy for short periods. These active galactic nuclei, AGN, are known to sculpt their environments, blowing out bubbles, launching jets that stretch for hundreds of thousands of light years, and driving shockwaves through interstellar and even intergalactic space. Given that, it's logical to wonder if the ORC phenomenon is a rare, extreme manifestation of black hole activity, some event where the outflow is perfectly spherical, inflating a bubble of relativistic particles that lights up the radio sky as a ring. There's precedent. We've seen enormous radio bubbles in systems like Centaurus A and the Milky Way's own Fermi bubbles. But those bubbles are messy, lumpy, and often connected to jets, or lobes, not isolated and sharply defined like an ORC. One possibility is that an unusual episode in a black hole's life, a sudden, isotropic, all-direction outburst, drives a nearly perfect shockwave into the galactic or intergalactic medium. In this rare scenario, the black hole's accretion disk might suddenly eject energy in all directions at once, rather than through narrow jets. The result? A vast spherical front of energized particles that could, under the right conditions, expand for millions of years and produce a radio ring visible billions of years later. But these kinds of outbursts are only theorized. We don't have confirmed examples in the nearby universe, and we don't understand what would cause a black hole to erupt so symmetrically. Another scenario is that repeated episodes of black hole activity, periodic feeding, followed by powerful outflows, could gradually inflate a massive, spherical radio halo. The particles trapped in these bubbles would spiral along magnetic fields, emitting synchrotron radiation, which is what radio telescopes detect. Over cosmic time, the energy could build up enough to create the ORC's enormous size. But again, if this were a common process, we'd expect to find radio rings or halos around many active galaxies, and that's just not what we see. In reality, the vast majority of known active galactic nuclei, even the most powerful radio galaxies in the universe, do not show ORCs. They might have double-lobed structures, elongated jets, and sometimes amorphous radio halos, but never the perfectly isolated circular rings that define an ORC. That means whatever triggers the ORC phenomenon must be an extremely rare, possibly short-lived, and highly specific event. One that almost never lines up with the usual ways black holes shape their galaxies. So, what's the missing ingredient? It might be a matter of timing. Perhaps ORCs represent a brief phase after a unique black hole outburst, one that fades too quickly to catch, except in the rarest of circumstances. It might be a question of environment. Perhaps only certain galaxies, surrounded by vast reservoirs of gas and embedded in just the right kind of intergalactic medium, can sustain a radio shell for long enough that we see it as a ring. Or maybe it's about the history of the galaxy. Only those that underwent specific sequences of mergers, starbursts, and black hole activity produce the necessary conditions. It's also possible that orientation plays a crucial role. If the black hole's outflow is not truly spherical, but slightly elongated, the ring might only be visible from certain angles, making most such events invisible or unrecognizable to us. This would dramatically reduce the number of ORCs we're likely to find, explaining their baffling rarity. Another layer of complexity is the physics of synchrotron emission itself. The radio glow comes from electrons accelerated to nearly the speed of light, spiraling along magnetic fields. Generating enough of these electrons and sustaining the right kind of magnetic structure over a volume as vast as an ORC might require circumstances astronomers haven't yet modelled, or even imagined. And there's one more problem. If ORCs are powered by black hole activity, what's stopping other energetic processes, like starburst-driven superwinds or cluster shocks, from making similar structures? We see lots of irregular halos and bubbles from those processes, but never anything as clean or symmetric as an ORC. This points to something unique about the central engine, the timing, or the galactic environment. All this leaves astronomers in a bind. The connection to supermassive black holes is tempting and logical, but the evidence is circumstantial and incomplete. ORCs might represent a heretofore unknown mode of black hole feedback, one that only switches on under extraordinarily specific conditions, and switches off so quickly that only a handful of examples are left glowing billions of years later. Or they might be something else entirely, a new class of object born from a process no one has yet theorized. What if, instead of being a rare type of known phenomenon, ORCs are actually the first examples of something completely new in astrophysics? Could these rings point to an entirely unexplored side of cosmic evolution, a process no one had even imagined before the last decade? Could odd radio circles truly represent a new type of cosmic phenomenon, something that not only hasn't been seen, but hadn't even been imagined in the theoretical playbook of astrophysics? This is where the discovery of ORCs rockets past the usual territory of cosmic mysteries and lands squarely in the realm of the unknown. Up to now, almost every major class of astronomical object, from galaxies to quasars, pulsars to gamma-ray bursts, was predicted, at least in outline, by some model or theory before it was observed. ORCs shattered that pattern. There's no equation, no simulation, and no scenario in the standard models of the universe that ever predicted enormous, symmetric, faint radio rings with no obvious cause. This absence of a theoretical home for ORCs means astronomers are forced to consider the possibility that these circles are not just oddities, not just rare versions of known objects, but the visible signature of an entirely new astrophysical process, one that plays out on a scale and in a regime never before explored. It's the kind of prospect that electrifies science, a chance to push the frontier, rewrite the textbooks, and reveal a chapter of the universe's story that no one suspected was missing. But how do you even begin to test hypotheses when you have fewer than a dozen examples and no precedent? Science moves forward by observation, replication, and falsification. Yet, with ORCs, there's barely enough data to outline a pattern, much less confirm a theory. Each new object discovered can upend months of speculation, and every unusual detail, slightly different brightness, a shifted center, a missing host galaxy, could mean a crucial difference in origin or structure. The approach, then, is to go back to basics and squeeze every drop of information from what we do have. Astronomers start by ruling out the ordinary. Could ORCs be artifacts, imaging errors, or combinations of faint overlapping sources masquerading as rings? Every candidate is cross-checked across multiple instruments with independent observations from different telescopes and data processing pipelines. Only those that persist through every test are kept as true ORCs. Next, researchers compare ORCs to every known category of object. Is the ring a distant supernova remnant? No, too large and not associated with the right kind of galaxy. Could it be a radio relic from a galaxy cluster? Again, no. The ORCs are more symmetric, isolated, and not found where relics are common. Is gravitational lensing at play, bending radio waves into a ring? That creates Einstein rings, but those are typically tiny, and they have distinct signatures that don't match the smooth, diffuse glow of an ORC. With known explanations exhausted, theorists start from scratch. Could the rings be caused by a process never previously identified? A new kind of cosmic shockwave, a unique interaction between magnetic fields and relativistic particles, or an entirely unfamiliar type of outflow from a galaxy's core? The size, symmetry, and rarity force theorists to think at galactic, or even larger scales, imagining processes that could inflate a radio-bright shell so vast, yet leave so little trace at other wavelengths. Some even push into the realm of the exotic. Could ORCs be signatures of dark matter interactions, or products of early universe physics, such as the decay of hypothetical cosmic strings, or relics of phase transitions that happened when the universe was young? These ideas are wild, but ORCs themselves are so unexpected that almost nothing can be ruled out without further data. To test such bold hypotheses, scientists deploy every tool in the modern astrophysical arsenal. High-resolution radio imaging maps the structure of each ORC in detail, searching for clues in faint filaments, brightness variations, or connections to other radio sources. Follow-up observations at other wavelengths, infrared, optical, X-ray, hunt for host galaxies, signatures of past explosions, or hints of unusual activity. Computer simulations are pushed to their limits, tweaking initial conditions, energies, and physical laws in search of any model that can reproduce the observed rings. But the bottleneck is always the same. So few examples, so much uncertainty. Each new ORC is precious data, but also a source of confusion if it doesn't fit the emerging pattern. Even the existing 8 show hints of diversity. Some are brighter, some fainter, some apparently hostless, others with a clear central galaxy. Do they all share a single origin? Or are multiple processes masquerading as the same phenomenon in our telescopes? What makes the case even more confounding is that the discovery of ORCs only happened with the latest generation of radio surveys. This opens up the terrifying possibility that the universe is littered with new, undetected classes of objects, their signals buried just beneath our threshold of sensitivity or hidden in the noise of incomplete data. It's a reminder that, despite centuries of mapping and modeling, the cosmos may be far stranger and more varied than our theories have allowed. The possibility that ORCs are the first members of a new, unpredicted class of cosmic object is both thrilling and humbling. The challenge now is to gather enough evidence, more discoveries, more detailed observations, more creative theories, to transform the idea from wild speculation into established science. Until then, the investigation continues, driven by a combination of relentless skepticism, technological innovation, and the exhilarating sense that we're standing on the edge of a new frontier. How, then, do scientists move forward in studying something so rare, so new, and so enigmatic? What methods are used to investigate a phenomenon with barely a handful of examples in the universe? How do you investigate a phenomenon so rare that you can count all known examples on your fingers? In the case of odd radio circles, with fewer than a dozen confirmed, every single discovery becomes a high-stakes event and a vital test of scientific rigor. The challenge is enormous. You can't rely on statistics, population studies or establish trends the way you would with supernovae, pulsars, or even fast radio bursts. Instead, every ORC must be scrutinized to the limit, because in such a data-starved field, even a single misidentification could mislead the entire scientific community. The first step is relentless skepticism. Each candidate ORC is subjected to exhaustive follow-up observations. Multiple radio telescopes, ASKAP, MIRKAT, and others, are aimed at the same patch of sky, and sometimes the same ORC at different times and frequencies. This ensures that what appears as a ring in one instrument isn't just a quirk of the technology, an imaging artifact, or a data processing glitch. If the circle persists across independent instruments, the odds of a false positive plummet. Next, astronomers cross-check the data with observations from completely different parts of the electromagnetic spectrum. If the radio ring is real, what do you see at optical, infrared, or X-ray? Wavelengths. Can you find a galaxy at the center? Is there evidence of a past explosion, merger, or energetic event? Are there traces of hot gas or unusual magnetic activity? This multi-wavelength approach is crucial because it helps rule out common culprits, such as supernova remnants, gravitational lenses, or nearby background sources that might masquerade as ORCs. Advanced simulations become essential. Researchers build models to mimic every plausible way a ring could appear in the data by chance. Could noise patterns, interference, or radio frequency contamination from Earth-based sources create a false ORC? What about overlapping emission from multiple faint sources? Do artifacts appear in certain data reduction pipelines that might produce phantom rings? Only after every technical and mundane explanation is eliminated do scientists tentatively admit the object into the exclusive club of genuine ORCs. But the threat of misinterpretation is real and ever-present. Astronomers are keenly aware of the pareidolia effect, the human tendency to see patterns, especially circles and faces, in random data. In radio astronomy, this can be amplified by the way images are reconstructed from raw signals, sometimes producing ghostly shapes out of pure statistical chance. For this reason, peer review and independent confirmation are mandatory. Every discovery is challenged by colleagues, double-checked against archival data, and sometimes even reprocessed by other research teams to confirm the reality of the object. Once an ORC is confirmed as a genuine astrophysical source, the scientific process shifts from skepticism to curiosity. Researchers design targeted follow-up campaigns, ultra-deep radio imaging to reveal fine structure, polarization measurements to probe magnetic fields, and spectroscopic studies to measure the properties of the host galaxy. These observations might uncover subtle features, faint filaments, shock fronts, or clues about the motion of the particles that help decode the physical processes at work. Computer simulations move into high gear as theorists try to match every observable detail. Can a model of a spherical shockwave from a galactic explosion reproduce the sharp edge and faint radio emission of an ORC? Do specific kinds of magnetic field structures create the right emission profile? How does the radio brightness evolve over millions of years? Every success and failure in simulation is a clue, narrowing down the range of possible explanations. With so few examples, researchers also scour the archives. Thousands of old radio images are re-examined using new search algorithms, looking for missed ORCs hiding in plain sight. Machine learning tools are increasingly used to scan massive sky surveys for ring-like features that might have been overlooked by the human eye. Sometimes, a faint candidate emerges, warranting further observation. Other times, the search comes up empty, reinforcing just how elusive these rings really are. And yet, even with all this rigor, the possibility lingers. Could ORCs be a subtle kind of cosmic illusion? Some critics have suggested that odd combinations of faint sources, rare radio, interference, or extreme gravitational lensing could create ring-like features under special circumstances. In response, astronomers have meticulously catalogued all known sources of contamination, run extensive null tests where no ORCs should appear, and developed new data processing pipelines to minimize the risk of artifacts. So far, every genuine ORC has passed these gauntlets, but the community remains vigilant. Until more are found, the risk of some systematic error, or an as yet unknown kind of misinterpretation, cannot be completely dismissed. This is what makes ORC research both exhilarating and fraught. Every new detection might be a revolution, but every confirmation is provisional, hanging on the next round of tests. Unlike more populous cosmic phenomena, the study of ORCs is conducted on the razor's edge of what's possible, balancing skepticism with curiosity, and always aware that a single data point could change the landscape overnight. But assuming ORCs are not illusions, the next challenge is even stranger. What, physically, are they made of? What exactly produces the ghostly radio emission from these enormous rings? And what does that tell us about the matter and forces at play within them? Is it possible that odd radio circles aren't real objects at all, but rather elaborate tricks of cosmic perspective or subtle illusions born from the quirks of astronomical data? In science, especially when peering into the extreme edges of detectability, this question isn't just reasonable, it's necessary. The history of astronomy is littered with discoveries later revealed to be mistakes. Planets that never existed, phantom stars, entire classes of objects born from image artifacts or instrumental noise. When an object is as rare, as unexpected, and as faint as an ORC, the burden of proof is enormous. From the moment the first ORC was reported, skeptics went to work. Could these rings be nothing more than a mirage in the data, created by the way radio telescopes process the faintest signals from the distant universe? Radio astronomy is inherently complex. The signals collected are transformed, reconstructed, and mapped using a process called interferometry. It's a mathematical and computational ballet, where the slightest miscalculation or miscalibration can create patterns that don't exist in reality, sometimes even rings, arcs, or halos. The temptation to ascribe ORCs to such image processing artifacts was strong, and it demanded a relentless audit. Astronomers attacked the problem from all sides. First, they looked for consistent signatures. Do ORCs appear only in a single survey, or do they persist across data taken with different telescopes, at different times, and with different instrument configurations? Genuine cosmic objects should remain, while artifacts and noise should change or disappear. The answer came quickly. Real ORCs showed up in multiple, completely independent datasets. ASCAP might spot an ORC first, but mere K, AT, or another radio array tuned to the same part of the sky would confirm it. The ring wouldn't shift, warp, or fade in any manner consistent with a processing glitch. If it was an illusion, it was being perfectly imitated by multiple technologies and independent observing runs. Next came the hunt for statistical anomalies. Could a combination of random noise, cosmic background radiation, or overlapping sources just happen to produce something ring-like, if only rarely? Researchers used powerful computers to simulate thousands of synthetic skies, each filled with randomly placed sources, noise spikes, and even known artifacts from radio observations. The results were clear. While random blobs, patches, and even lines could appear, true, symmetric, and sharply defined rings of the size and scale of ORCs almost never did. When rings did emerge from the data, they were orders of magnitude smaller, fuzzier, or obviously tied to known sources, never matching the precision or enormity of an ORC. The next check was gravitational lensing. The universe is filled with massive objects, galaxies, galaxy clusters that can bend light and radio waves through gravity, sometimes creating beautiful and eerie rings known as Einstein rings. These are real and have fooled astronomers before. But Einstein rings are formed by the bending of light from a background source, often a quasar, into a ring by a massive foreground object. Their size is typically tiny compared to ORCs, and their structure is sharply defined, often with a source at the center that is visible in multiple wavelengths. Detailed analysis of ORCs revealed no such alignment. The candidate host galaxies are almost always in the center, not acting as a lens, and the scale is vastly larger than even the most powerful gravitational lenses known. The spectrum and surface brightness profiles of ORCs simply don't match the textbook case for lensing. Another candidate for cosmic illusion was interference or contamination from terrestrial sources. Everything from satellite transmissions, cell phone towers, radar, to reflections from high-altitude airplanes. Radio astronomers are well versed in these terrestrial threats and design extensive radio-quiet protocols to avoid them. Every ORC candidate has been checked against logs of satellite overflights, terrestrial emissions, and even subtle frequency spikes. No terrestrial culprit has ever explained an ORC, especially given their reproducibility across continents and years. Peer review added another wall of scrutiny. Each ORC discovery was not only challenged by the original observers, but also by external teams. When the discovery team found a ring, other groups with access to the same raw data reprocessed it from scratch, using different calibration software, different denoising routines, and even alternative data formats. The ORCs persisted, immune to all but the most basic image distortions, like flipping the entire map upside down. Statistical analyses of false positives, null fields, and control samples showed that the odds of even a single ORC being a trick of the data were vanishingly small. Still, science demands relentless skepticism. Could something new about the universe, or something overlooked in the software, be conspiring to create a shared illusion? Astronomers responded by going beyond the data itself, looking at what else might be visible at the location of an ORC. Deep optical and infrared imaging campaigns searched for host galaxies, potential background objects, or odd alignments that might have slipped past radio-only analyses. In nearly every confirmed case, a galaxy was found at the geometric center of the ring. Further, supporting the idea that ORCs are not random, but physical, cosmic structures with a point of origin. But even after passing all these tests, the question remained: if ORCs are real, what are they made of? The radio emission isn't just a glow. It's a specific kind of signal known as synchrotron radiation, which only happens when high-speed electrons spiral through strong magnetic fields. This means the fabric of an ORC is not made of normal starlight or even warm gas. but of a vast halo of relativistic particles, electrons moving near the speed of light, caught in magnetic fields stretching over hundreds of thousands of light years. This composition itself was a surprise. Synchrotron radiation is common in active galaxies, supernova remnants, and cosmic jets, but always in more compact, more structured, or more chaotic environments. For a shell this enormous to shine in radio, there must be a mechanism injecting tremendous energy into a precisely shaped volume of intergalactic space and sustaining the magnetic fields required for synchrotron emission. The presence of this radiation, confirmed by polarization studies and spectral analysis, is another piece of evidence against the illusion hypothesis. Illusions can't fake a specific emission mechanism that requires particular physics. Even the faintness of ORCs works against the case for illusion. If you were to construct an artifact by overlapping enough faint sources, noise, and calibration quirks to mimic a ring, you'd expect it to appear more irregular, more variable, or at least more common. The fact that ORCs are almost unnaturally symmetric, stable over time, and staggeringly rare argues that they are a genuine, if deeply enigmatic, population. Nonetheless, astronomers remain vigilant. New candidates are scrutinized, new calibration routines are run, and new types of cross-checks are invented each year. The process is iterative. As more ORCs are found, and as telescopes become more sensitive, the risk of subtle errors decreases, but never disappears entirely. As the sample grows, scientists can compare properties. Does every ORC have a host galaxy? Do their sizes and surface brightnesses follow a predictable trend? Are there partial ORCs, or are the rings always complete? Patterns, or the lack thereof, will further sharpen the distinction between reality and artifact. The real possibility that ORCs are genuine cosmic structures is now the consensus. But every answer only triggers deeper questions. If these ghostly rings are real, what else can we say about their substance? What are they really made of, on the microscopic and macroscopic scale? How do so many electrons get accelerated to such high energies, and what does that say about the events that triggered them? If the synchrotron glow is the after effect, what was the original explosion or disturbance? To solve that puzzle, scientists turn next to probing the composition of ORCs, digging into the very nature of the particles, fields, and energies that animate these gigantic, invisible halos. Understanding their makeup could be the key to unraveling not just the story of the ORCs themselves, but the deeper physics of galaxies, black holes, and cosmic shocks. What precisely are odd radio circles made of? If they're not illusions or artifacts, and their ghostly presence is confirmed across multiple instruments and wavelengths, what is actually glowing out there across hundreds of thousands of light years? The simple answer, at least the only one that fits the data so far, is that ORCs are not made of ordinary gas or clouds of stars. Instead, their radio glow is the unmistakable fingerprint of a much more exotic process. Clouds of high energy, or relativistic, electrons spiraling through cosmic magnetic fields at nearly the speed of light. This emission, known as synchrotron radiation, isn't unique to ORCs. It's a familiar signature across the universe, found wherever electrons are accelerated by powerful forces. Supernova remnants, the jets and lobes of radio galaxies, pulsar wind nebulae, and the aftermaths of some of the most energetic explosions in the cosmos. But in every other case, the origin of the electrons and the magnetic fields is at least partly understood. Supernovae accelerate particles through shockwaves. Black hole jets funnel them along tightly focused streams. galaxy clusters are suffused with hot plasma and tangled fields. With ORCs, the scale and context break the mold. The sheer size of these rings, sometimes more than 1,000,000 light-years across, implies a titanic energy input, sustained or unleashed across a region larger than entire galaxy clusters. And yet, their faintness suggests that the process is either astonishingly diffuse or ancient, with the energetic particles gradually fading away, radiating their last photons before disappearing into the cosmic background. But if ORCs are fossils of ancient cosmic events, the nature of the event must have been unprecedented. Some combination of explosive power, symmetry, and scale that no known mechanism has managed to replicate in nearby space. So, what do astronomers know about the composition of ORCs? Observations confirm the presence of synchrotron emission, which requires two things: fast-moving electrons and magnetic fields strong enough to force those electrons into tight spirals. Polarization measurements, where the orientation of the radio waves is analyzed, reveal ordered patterns, indicating coherent, large-scale magnetic structures. But here's the paradox: the amount of gas, dust, or other normal matter detected within the ORCs is nowhere near enough to account for their scale and radioluminosity. In fact, most ORCs seem to float in cosmic voids, with only the faintest hint of diffuse hydrogen or intergalactic plasma. This raises the inevitable question: what injected the energy, and what sustains it? If it was simply gas, heated by a shockwave, we'd expect to see thermal emission at other wavelengths: infrared, X-ray, or optical. But for most ORCs, the non-radio signal is either entirely absent or orders of magnitude too weak to fit the standard models. The implication is clear: whatever formed the ORCs must have directly accelerated vast quantities of electrons to near light speed and organized them into a shell-like structure, all while leaving little or no trace in the other electromagnetic windows. Could dark matter or some even more exotic form of physics be responsible? While there's no direct evidence yet, the door can't be closed. Dark matter is thought to outweigh all visible matter in the universe by a factor of 5. Yet it emits no light and interacts only weakly through gravity. Theoretical models have suggested scenarios where dark matter could, under rare circumstances, interact with itself or with ordinary matter in ways that might produce bursts of energetic particles, possibly lighting up as faint extended radio structures. This is highly speculative and not yet backed by any specific features in ORC observations. But it's a reminder of how little is truly ruled out in such uncharted territory. Another radical idea is that ORCs are powered by decay or annihilation of exotic particles, perhaps relics from the early universe, or the result of as yet unseen processes during cosmic phase transitions. In these scenarios, energy would be injected into intergalactic space not by explosions or black hole activity, but by the transformation of fundamental fields or the destruction of massive particles. While these hypotheses are at the very frontier of modern cosmology, they provide a conceptual framework for why ORCs appear only at great distances and thus early times in cosmic history, and why their properties are so uniform yet so hard to connect with ordinary galactic or cluster activity. Still, the more conservative camp in astronomy sticks with normal physics pushed to an extreme. Maybe the electrons were accelerated by a vast spherical shockwave from a once-in-a-billion-year event, a massive galaxy merger, a unique burst of black hole activity, or an encounter between a galaxy and an unusually dense patch of the cosmic web. In this case, the energy needed is extreme, but not unthinkable. And the ORC's symmetry is a relic of the physics of shock propagation, radiative cooling, and the expansion of energetic shells through tenuous intergalactic medium. The mechanism for organizing the electrons and magnetic fields into such a clean, circular shell is still a major unknown. No other known astrophysical process produces structures with the same combination of scale, symmetry, and faintness. Magnetic fields themselves are notoriously difficult to map, but the polarization data from some ORCs suggests a degree of order and coherence across unimaginable distances. Did the event that created the ORC also amplify or arrange the fields? Or is the symmetry a projection effect, with the shell only appearing perfect from our unique vantage point? Adding to the puzzle, there's no sign that the host galaxies at the center of most ORCs are still energetic enough to be producing new electrons or maintaining active magnetic structures. Whatever happened, it appears to be over, leaving only the slowly fading, radio-bright afterglow as evidence. The absence of continued activity makes ORCs a kind of cosmic crime scene. The main event is finished, and all that remains are the cold clues scattered across intergalactic space. Are there still more exotic explanations left? Absolutely. Some researchers speculate about topological defects in space itself, like cosmic strings, hypothetical remnants from the Big Bang, interacting in rare, spectacular events to produce spherical shells of energy. Others point to the possibility that the radio emission is a byproduct of as yet unknown forms of plasma instability or turbulence in the intergalactic medium, triggered by ancient phenomena that simply don't occur in the modern universe. In the end, the best evidence is still what's observed: enormous faint radio rings composed of relativistic electrons and magnetic fields, with little to no visible matter involved, and no ongoing source of energy. The simplicity and regularity of the radio emission are as startling as the scale. The silence at other wavelengths is as telling as the faint signal that radio astronomers chase across the sky. Cracking the composition of ORCs is more than an academic exercise. Understanding what fills these ghostly halos could answer deeper questions. How do galaxies evolve and interact with their environment? What processes shape the magnetic fields and energetic particles that pervade the cosmos? Are there hidden forms of matter or energy still at work in the universe, invisible except for their fleeting radio glow? And above all, what does the perfect, almost mathematical symmetry of ORCs say about the forces that created them? Why do they appear as near-perfect circles in a universe known for its chaos and asymmetry? Why are odd radio circles so strikingly symmetrical? This is one of the most haunting features about ORCs, and it's not an exaggeration to say that their near-perfect circularity is what pushed astronomers to take them seriously as a brand new cosmic puzzle. The universe is chaotic. Galaxies are warped and lopsided. Supernova remnants are shredded and turbulent. Jets from black holes twist and bend. Very few things in the cosmos are truly round, especially when viewed at massive scales. Yet, when an ORC appears in a radio image, it's a geometry lesson written in starlight, an almost mathematically perfect circle, sometimes so precise it looks computer-generated. What on earth, or rather, what in the universe, could create something this symmetrical? The dominant hypothesis points toward a spherical origin, and the most natural candidate is a shockwave, a massive blast wave propagating outward from some explosive event. When a powerful outburst happens in the thin plasma between galaxies, the energy expands in all directions, forming a shell. From our vantage point, looking straight through the edges of that shell, we see the densest cross-section of energetic particles and magnetic fields, which produces the brightest ring. It's the same principle that makes the rim of a soap bubble or the edge of a smoke ring look brighter than the rest of the surface. In 3 dimensions, ORCs are probably enormous spherical shells, but our 2-dimensional images only capture their cross-sectional circles. But here's where the mystery deepens. Real cosmic shockwaves, whether from supernovae, galaxy collisions, or black hole outbursts, are never this tidy. They encounter clumps of gas, magnetic turbulence, gravitational distortions, and other nearby galaxies that disrupt their shape. Even in the rare cases where spherical outflows do form, like the shells of some supernova remnants, the resulting structures are always bumpy, wrinkled, or incomplete, often shredded by the chaos of interstellar or intergalactic environments. The intergalactic medium through which an ORC shell would travel is filled with matter, fields, and unseen obstacles. Over hundreds of thousands or even millions of years, it's almost impossible for any structure to stay perfectly round. Yet, ORCs defy this expectation. Their edges are astonishingly smooth, and their circularity holds up under high-resolution scrutiny. No obvious filaments, knots, or distortions break the pattern. This tells astronomers 2 things. First, whatever event created the ORC, it must have occurred in a relatively empty environment. One with so little resistance that the shockwave could propagate cleanly for hundreds of thousands of light years without being torn apart. That suggests a birth in the voids between galaxies, or in regions with exceptionally low density. Second, the force that shaped the ORC must have been nearly isotropic, energy released evenly in all directions, unlike the focused jets seen from black holes or the irregular blasts from most galaxy mergers. The symmetry also hints at a short timescale for formation. If the structure had lingered for too long, or if it had been formed in multiple stages, there would be more time and more opportunity for gravitational tides, ram pressure, and turbulence to break the ring apart. The fact that we see ORCs as complete, unbroken circles suggests the energetic event was both recent, at least in cosmic terms, and fast-acting, inflating a bubble in a single, coherent explosion or outflow. Is it possible that projection effects are exaggerating the symmetry? In astronomy, 3-dimensional objects viewed from specific angles can sometimes appear more regular than they are. A spherical shell, even with some irregularities, may still look very round if we're observing it at just the right orientation. But statistical models show that the odds of finding so many ORCs with such perfect symmetry and always nearly face-on are slim. If there were hundreds of ORCs with varied shapes and angles, we might chalk it up to selection bias, but with so few and all so close to ideal circles, the message is clear. The underlying process is fundamentally symmetric. Polarization studies offer another clue. When astronomers analyze the directionality of the radio emission, they sometimes find evidence of highly ordered magnetic fields aligned with the shell of the ORC. This degree of organization over such a vast distance is rare and reinforces the idea of a massive, coherent shockwave, possibly interacting with a pre-existing field. It's as if the original event not only shaped the electrons into a shell, but also arranged the magnetic fields into near-perfect alignment. The symmetry of ORCs is more than just a curiosity. It's a diagnostic tool. The more perfectly round a structure, the more clues it provides about the nature of the force that shaped it. In astrophysics, true circles almost always mean either a spherical explosion, a shock wave moving at the same speed in all directions, or a resonant phenomenon where energy is distributed with uncanny uniformity. All of these are rare, but not impossible, under just the right cosmic conditions. What does this tell us about the forces involved? The event that created an ORC was likely an explosive, short-lived outburst releasing energy on a scale that dwarfs any known stellar process. The environment had to be nearly empty, with little to slow or deform the expanding shell. And the magnetic fields, either pre-existing or generated by the explosion, had to be organized enough to channel electrons in a clean, coherent shell. But the lingering question is, why are such events so rare? If all the ingredients occasionally align in the universe, we might expect to see a spectrum of shells and rings in various stages of distortion. Yet, ORCs seem to jump straight from non-existence to perfection. It suggests a Goldilocks zone of physics, an event so uncommon and an environment so particular that only a handful of these radio rings have formed over billions of years. As astronomers continue to hunt for more ORCs, their symmetry remains the most tantalizing and frustrating clue. It hints at extreme, perhaps unique, physical processes at play, forces powerful enough to reshape vast regions of intergalactic space, yet subtle enough to fade into ghostly silence in every wavelength except radio. But if we can decode that symmetry, understand what physical law or cataclysmic event could sculpt such perfection from the chaos of the universe, we might unlock answers not just about the ORCs themselves, but about the evolution of galaxies, the hidden workings of cosmic magnetism, and even the fundamental rules that shape the large-scale universe. So, if ORCs are the fingerprints of some unknown cosmic event, what do they tell us about the broader universe? What secrets could these silent, perfect circles help us reveal about the history and evolution of everything we see in the sky? If we can solve the mystery of odd radio circles, what broader secrets might they unlock about the cosmos? ORCs aren't just another astronomical curiosity to be catalogued and filed away. Their very existence challenges our understanding of how galaxies evolve, how energy is distributed across intergalactic space, and how magnetic fields, the hidden scaffolding of the universe, can be shaped and preserved over unimaginable distances. In the history of astronomy, every time we've encountered a phenomenon that doesn't fit, it's forced us to rethink fundamental assumptions. ORCs might be the next such breakthrough, a gateway to entirely new realms of cosmic physics. First, consider what their presence implies for galaxy evolution. If ORCs are indeed the remnants of colossal explosions, black hole outbursts, or other extreme galactic events, they are evidence of feedback processes operating on scales far larger than anything previously observed. Feedback is the mechanism by which galaxies regulate their own growth. Black holes and starbursts inject energy into their surroundings, preventing runaway star formation and redistributing matter. Until now, this feedback was thought to be confined mostly to the galaxy itself, perhaps leaking a bit into the surrounding halo. But an ORC, stretching 1,000,000 light-years from its host, suggests that the consequences of these energetic events can reach deep into intergalactic space, shaping the large-scale structure of the universe and influencing the fate of other galaxies far beyond their own boundaries. If ORCs are the fossil records of long-ago mergers or black hole eruptions, They might provide a missing link in understanding why galaxies look and behave as they do today. For example, they could explain why some galaxies stop forming stars earlier than others, or why the cosmic web appears patchy and irregular on the largest scales. They might even illuminate the history of cosmic downsizing, the process by which the universe's largest structures formed early and evolved more rapidly than smaller ones. But the implications stretch far beyond galaxy evolution. ORCs are among the cleanest, most gigantic laboratories we have for studying cosmic magnetism, a force that shapes everything from star formation to the motion of gas in clusters. Mapping the polarization of their radio emission could reveal how intergalactic magnetic fields are organized, how they're amplified, and how they persist over billions of years. These fields are otherwise nearly invisible. ORCs give us a rare and precious chance to see them illuminated, if only for a brief cosmic moment. There's also the tantalizing possibility that ORCs are a window into the truly exotic. If their formation involves dark matter, exotic particles, or new plasma processes, solving their mystery could open an entirely new front in our understanding of the universe's hidden components. This is not a wild fantasy. Historically, radio astronomy has been the first to reveal phenomena later found to be crucial to physics: pulsars, quasars, the cosmic microwave background. ORCs could be the heralds of another such revolution, showing us that our current models are incomplete. Even their rarity and distribution are clues. The fact that all known ORCs are billions of light years away, and thus seen as they were billions of years ago, suggests that the universe itself was once more prone to whatever process creates them. Perhaps the conditions for ORC formation have passed as galaxies settled down and the cosmic web matured. Or maybe our instruments are only just now becoming sensitive enough to glimpse these faint echoes from a rowdier cosmic past. Each new detection, or lack thereof, will refine our understanding not just of ORCs, but of cosmic history itself. The search for answers is driving a new era in radio astronomy. Researchers are now combing through archival data with advanced algorithms and machine learning, hunting for missed rings in old surveys. New instruments, including the massive Square Kilometre Array currently under construction, will soon probe the radio universe with unprecedented sensitivity and speed. If ORCs are out there in greater numbers, we may be on the verge of a flood of discoveries that will provide the statistical power needed to decode their origins. And it doesn't stop with the radio sky. Teams are following up with deep optical, infrared, and X-ray observations, hunting for associated phenomena, fading afterglows, hot gas, or even bursts of gravitational waves that might point to the most energetic mergers. Every piece of data is another puzzle piece in a picture that, for now, remains stunningly incomplete. As with every cosmic riddle, the solution to ORCs will likely rewrite more than just one chapter of astronomy. It may transform how we think about feedback in galaxies, the reach of black holes, the nature of cosmic magnetism, or the behavior of dark matter and plasma in the deepest voids. The lesson of astronomy is always this: the rarest things, once understood, are the most revealing. But the investigation is far from over. The next step is the relentless, methodical hunt for new ORCs using the most advanced technology ever built, and the open-minded persistence to recognize a new phenomenon even when it doesn't fit our expectations. Could we be on the verge of finding hundreds more, or will ORCs remain one of the rarest cosmic signatures in existence? What's next for the search for odd radio circles? The mystery of ORCs has pushed astronomers into a new era of sky surveys, demanding tools and strategies unlike anything used before. For the first time, the entire community is on the hunt for the rarest of cosmic fingerprints, knowing that every new ring could change everything we think we know about galaxies, black holes, and the structure of the universe itself. But this hunt is just beginning, and the road ahead is both daunting and thrilling. The biggest leap forward will come with the next generation of radio observatories. Massive, globally coordinated projects designed to scan the sky deeper, faster, and with more precision than ever before. At the heart of this new wave is the Square Kilometre Array, SKA, an international effort now under construction in Australia and South Africa. When completed, SKA will be the largest radio telescope array on Earth, combining thousands of antennas spread over entire continents to create an effective collecting area of 1 square kilometre. This scale will enable astronomers to capture faint, diffuse, and extended radio features with exquisite detail, exactly the kind of signals that define ORCs. With SKA, astronomers expect to move from the era of accidental discovery to systematic census. Rather than stumbling upon ORCs while looking for something else, researchers will be able to design surveys specifically optimized to find circular, low-surface brightness radio halos. The unprecedented sensitivity and resolution of SKA, especially at low radio frequencies, will allow it to sweep enormous volumes of space, picking up even the faintest and most ancient radio rings. Where today only 8 ORCs are known, within a decade, hundreds or even thousands could emerge from the noise, allowing scientists to finally build the statistical samples needed to crack their origins. But SKA isn't working alone. Other new and upgraded facilities, such as MeerKT in South Africa, LOFAR in Europe, and the next upgrades to ASCAP in Australia, are already generating huge new datasets, many of which are still being mined for overlooked ORCs. The synergy between these observatories is crucial. What one telescope misses because of frequency range or sensitivity, another can catch. Multi-telescope campaigns can also confirm the reality of faint candidates, eliminating the chance of artifacts or noise masquerading as rings. Crucially, astronomers are deploying powerful new computational methods. Artificial intelligence and machine learning algorithms are now trained to recognize the specific fingerprint of an ORC in radio images, flagging candidate rings that might be invisible to the human eye. These systems can comb through petabytes of archival and live data, searching for the circular symmetry and low brightness features that define ORCs, even in the presence of background noise and confusion from more common sources. What was once a painstaking manual process, requiring astronomers to pore over image after image, can now be done in hours, greatly increasing the odds of new discoveries. Follow-up is another key frontier. The radio ring is just the beginning. To understand each ORC's origin, astronomers will need to probe its central galaxy, its environment, and any associated phenomena at other wavelengths. Deep optical and infrared surveys can reveal the type and state of the host galaxy. Is it a relic of a merger? An active galactic nucleus? An unusually massive or gas-rich system? X-ray and gamma-ray observatories will search for traces of past explosions, jets, or outflows, looking for signatures that match or challenge the theories of how ORCs are born. Even gravitational wave detectors may someday contribute if the explosive events that produce ORCs are also strong sources of space-time ripples. With these tools, researchers hope to answer the burning questions. Are ORCs all the aftermath of a single, rare type of cosmic event? Are there subclasses with different origins hidden behind their visual similarity? Why do they appear so far away in space and time? And will any ever be found closer to home? Are we on the brink of finding hundreds, maybe thousands, more? Or will the ORC remain one of the universe's most elusive signatures, detectable only in the quiet radio light of the distant cosmos? The flood of new data may bring surprises. The discovery of a single ORC in the local universe, for example, would force astronomers to reconsider the evolutionary timeline of these phenomena. Alternatively, finding a large population at similar redshifts could point to a cosmic epoch, especially rich in ORC-forming events. A period in the universe's history that was, for reasons yet unknown, uniquely prone to unleashing the forces capable of sculpting these colossal rings. Of course, the search isn't just about numbers. Every new ORC provides an opportunity to study how matter, energy, and magnetic fields interact on the largest possible scales. The discovery of variants, partial rings, double shells, or ORCs with unusual host galaxies could help break the theoretical deadlock and point towards specific origins. Even the distribution of ORCs across the sky, their sizes, and the environments in which they're found will help test the limits of our current models. What if, after all the advances, the universe still refuses to yield more ORCs? That possibility would be just as profound as a sudden deluge. It would cement ORCs as some of the rarest and most exotic phenomena in existence, forcing astronomers to look even harder at the tiny window of conditions and events capable of producing them. The absence of new discoveries is, itself a clue, narrowing down the list of candidates and increasing the importance of every detail gleaned from the handful we've already found. In the end, the search for ORCs is a story of relentless curiosity, technological innovation, and the willingness to confront the unknown. Whether the next few years bring a flood of discoveries or only a trickle, one thing is certain: every new ring in the cosmic dark is a message from the universe's wildest days, and decoding those messages will reveal truths that reach far beyond the fate of a handful of mysterious circles. The story of ORCs is far from over. As the new generation of telescopes comes online and the next wave of astronomers joins the hunt, the universe's rarest rings may finally yield their secrets, or strike out even deeper mysteries than we can imagine today. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.